Are you guys ready for some physics? Let's do some physics. We're in electrodynamics. I'm going through Griffiths. I'm in chapter 5 doing magnetostatics. We're calculating magnetic fields. So here we have this very important thing. This is the solenoid. I'll go ahead and tell you, spoiler alert, it's the capacitor of magnetic fields. So just like the capacitor made a constant electric field to some degree, approximation, this makes a constant magnetic field inside to some degree. But we're going to actually calculate the magnetic field due to this solenoid 3 ways. So number 1, we're going to do Ampere's law. Number 2, I'm going to use Biot-Savart and integrate. And then you know what's going to happen. Number 3, I'm going to do numerical calculation with Python. Let's get started. What are we doing? What we're doing wasting our time. We got to get started. We got lots to do. Lots to do here. Let's start off with Ampere's law though, because it's just the easiest. I wrote down some stuff. Here's my solenoid. It has a radius r, length l, lowercase n turns per length. So that's total number of turns in. And it has a current I going through there. We want to find the magnetic field anywhere along the z-axis. But right now we're going to start it in the middle of the solenoid. We're going to assume it's long and skinny because, again, to use Ampere's law, you have to know something about the field. You have to have some type of symmetry. I wrote down this because that's the magnetic field due to a loop, a single loop on the z-axis. We're going to need that. I derived that in a previous video. I'm pointing down there like it's down there somewhere, but if you can't find it, text or comment down below, and I will make sure that you have it. Okay. I'm going to draw another picture of my solenoid. So here's a solenoid view from the side. So suppose the current's going this way. So I have a bunch of wires. If I cut it in half up there, I have a bunch of wires down here. So these wires up here, and let's assume it's skinny and long. Skinny and long is super important. Okay. So let's suppose that the current's coming out of the page up here and into the board down there. So it's coming this way and then that way. But they're equal currents. So up here, if I look at one wire, okay, just one wire, this one wire, it's going to make a magnetic field. If the wire is coming this way, it's going to make a B. I'm going to call this B upper that way. And it's going to make B upper that way. Now, the bottom wire is going to make a magnetic field into the board. So inside up here, it's going to make a magnetic field B lower going that way. And up here, it's also still the same way, B lower. So if this thing's really skinny, then these two magnetic fields are going to cancel on the outside because the magnetic field due to the upper wire switches directions out that way. But inside, they're going to add up. And then the same thing would be true down here. Here I have B lower that way outside. And then I have B upper like that, and they cancel. They don't actually cancel. They just mostly cancel. Okay. But as an approximation, we get no magnetic field outside, and then we're going to get all these magnetic fields are going to be adding in the same direction and add up. So we get a constant magnetic field on the inside in that direction. And no magnetic field outside. That's important. Okay. So now let's just delete those labels. And once we have a situation where we have symmetry or we know something about the magnetic field, now we can use Ampere's law. So Ampere's law says that B dot dl around any closed path is equal to mu naught times I in the current passing through an area bounded by that path. So we just have to choose something that makes sense here. So let's choose a path that we can take advantage of the symmetry of the situation. Let's draw this in a different color. Purple seems nice. So here's my path. I'm going to go up, over, down, back. And this is going to be a length. I'm going to call that S. So now all I have to do is integrate B dot dl around that path. Well, I can do that. So I have 4 pieces. So if I go right here to there, I'm going in the same direction. B is constant. B is in the same direction as the path length. So I get BS. So that's this length. Right here, now B is that way, but DL is that way. They're in right angles to each other, so B dot DL is 0. And then on this part, B is 0. So I have 0 plus 0 is 0. Now on this part going this way, we said B was 0 over there, so it doesn't really matter, 0. And then up here I get 0, and then it's perpendicular again, so 0. So B dot dl is just B times S. That's going to be equal to mu naught times In. So how much current passes through there? Well, if I know there are lowercase n turns per length, then I can get the total current as I times N times S. NS tells me how many turns are in there, then I'm including in my path, and then I is total current. Oh, look at that. S cancels. So I get B equals mu naught N I. Or you could write that as mu naught N over L I. So that's the magnetic field. That's the magnitude of the magnetic field. Remember, we already said something about the direction. We already made a choice about the direction of that magnetic field. There, that's better. To get that value. I'm going to put it over here because it's going to be a result that we'll check later. Mu naught N I. That's the magnetic field in the loop. But again, we made some assumptions about the symmetry and the direction, so we don't get a vector value. That one's not too hard. Okay, now you're ready for hard. So I want to erase some stuff. So let's put this over here. I think I need more room. BZ mu naught I r squared over 2 r squared plus z squared to the 3/2. That's the magnetic field due to a loop along the axis. So if I can imagine this as being a bunch of loops along this axis, right? So let's just redraw this whole picture just so we can make it more useful. So I'm going to use this. Here's my coordinate system. So this is the z direction. And this is the point. And we're going to call that a distance d away. Okay. And then here's my solenoid like this. And I'm going to break this into, I'll put it over here, a ring. And so this ring has a location of z. And I want to find the magnetic field due to that. I want to write it down as a value. Now remember that we already found the magnetic field was in the z direction on the axis of that ring. So I'm just finding the z component. I already did that. Again, see the video down below. So the magnetic field due to that ring at this location, dB, it's in the z direction, I'm going to call it dB, is going to be equal to this. This is that ring. So I have mu naught I r squared. I have, that's not quite right. And then I'm going to have to get this z is the distance from here to there. So let's write this down. Mu naught di, right? Because not all the current flows through that thing, so we have to write that as di. R squared, that's the radius of the solenoid. 2 is the number 2. R squared. Now this distance, if this is d and this is z, this is d minus z. So plus d minus z quantity squared. And all of that to the 3/2 power. So that's my magnetic field just due to that one ring. Now, again, we can go back to this. The total current in there, the total current di, is going to be the total current I times n times the length of that thing. Well, the length of that thing is dz. So this is my current di up there. But you notice something really nice happened. dz is my integration variable, and I'm integrating over z. So I can't integrate over I if I have z right there. So I guess I should write that out. So I get mu naught I in r squared dz, making sure I don't miss anything, all of that over 2 r squared plus d minus z quantity squared to the 3/2. Now this is going to, we need to integrate to find the total magnetic field, and we're going to go from z as negative L over 2 to L over 2. I centered this on the origin. You don't have to do that, but it just makes it a little bit easier. So now I just need to integrate. So B, I'm going to pull all the constant stuff out front. Mu naught I in r squared over 2 times the integral from z equals negative L over 2 to z equals L over 2 of dz over r squared plus d minus z quantity squared. All of that to the 3/2. Now, that's a tough integral. Okay, and we actually did r squared plus z squared to the 3/2 before in a previous problem, and I said, oh, well, you got to look that up in the integral table, and I left my integral table getting it. And you can look this up however you like, but again, that's my CRC math tables handbook, and it has the math tables in there. We're looking at numbers 165 right there. You see it? Can you see it now? Now can you see it? Okay. So that's in terms of, I got to take off my glasses. Well, I don't have to in just a second. That has a x squared plus a squared, where a is a constant. So we have this squared plus a constant. So we need to do a quick, simple u substitution. So I'm going to say u is d minus z. So du is going to be negative dz. So I'm going to get a negative sign up here. I'm going to integrate. I'm going to leave the limits of integration the same, and then we can switch back to z to evaluate the limits. So this is going to be equal to negative mu naught I in r squared over 2 integral. I'm just going to leave it generic integral, and I'm running out of room right there. Ugh. Okay, I'll put it over here then. That's fine. Barrier. So b is negative mu naught I in r squared to the integral of du over r squared plus u squared to the 3/2. Now I can integrate that. I get mu naught I in r squared over 2. I'm going to do a double whammy here because it's just integration. we don't really care about it. I'm going to do a double whammy. I'm going to integrate and resubstitute back in my z. Okay, this one I do have to take my glasses off for just so I can see it. Okay, so I get x on the top, which is u. So u is d minus z. So I get d minus z over a squared, which is r squared, times the square root of x squared, which is d minus z squared, plus r squared. Evaluate, so I switch back to the z, so now I can evaluate from negative L over 2 to L over 2. Good? Good. Okay. Now we just need to evaluate the limits. Notice right away that I can cancel that. If I can cancel something, I can. That's an n, not a mu. Okay. So now I get b equals mu naught I in over 2. I'm going to put in L over 2. So I get d minus L over 2 over the square root of d minus L over 2 squared plus r squared. And then minus this, so I get minus negative, I get minus d plus L over 2 over the square root of d plus L over 2 quantity squared plus r squared. That's it. That's the answer. That is the answer. We should probably put a box around that. Let's do this hyper orange color right there. Look, it's boxed. It's official. Okay. Now, we do want to do one thing. What if I am in the center where the magnetic field is constant? Does this agree with this? I should put a different color box around that, right? Because that's not fair. Okay. So let's take the approximation, and we're going to need this for our numerical calculation too. Let's take the approximation that's really long, right, and really skinny. So, and I'm at the center. Because if it's really long, everywhere is the center, right? So I'm at the center, so d is equal to 0, and L is much larger than R. So d equals 0, and then L is greater than R. So if I put that in down here, I get b equals mu naught I in over 2, and then d is 0, so I get negative L over 2, And then down here, d is 0, so I have L squared over 2, L over 2 squared plus R squared. But L is much greater than R, so it's just going to be L squared over L over 2 squared, square rooted. So I get L over 2. And then I have minus, there was a negative sign here. Okay. I knew that because I'm like, this is going in the wrong direction. Minus L over 2 over 0 plus L over 2 squared plus R squared. But again, that's just L over 2. So this becomes negative 1 minus 1, so negative 2. So I get negative mu naught I in 2 over 2. Now the direction doesn't really matter. Oh, this is negative, so I do get plus. The 2's cancel. Same thing. So that's good, right? So that's good. Okay. Now we need to do this numerically. So numerically what we're going to do, and I did this before, I'm going to build a system of rings. And each one of those rings, we already did a ring, and I'm going to start with that ring. And I'm just going to put a bunch of rings in a row to make a solenoid, and then I can calculate the magnetic field. Going to be awesome. Let's just do it. Let's just jump into it. Okay, so I'm taking off my glasses. That means I'm doing some serious stuff here. Now, I copied some code from my previous situation, and I'm going to run it. So this is a loop. See my loop? Loop of current. And then I can calculate the magnetic field anywhere. Okay, so I broke it into loop. I'm going to keep it that way. The one thing I want to change is this loop has an axis in the z direction, and that's fine. I should keep it that way. But I like to rotate it sideways just because that's where you normally see a solenoid. So that's what I'm going to do first, and then I'm going to make a bunch of these loops. So right up here, n theta, n is the number of, so there's a problem right there. N is the number of loops, pieces in my loop. So I'm going to have some other things up here. Let's say n is equal to 1,000. That's my number of turns in the whole thing. Okay, and I'm going to need L. L is equal to, let's say 0. R is 1. 0.1, and let's make this 0.03. I don't know, I'm just picking some stuff here. Okay. Now I make a list of all my arrows that are IDLs. They're my DLs, they don't have I. And let's just go ahead and calculate N too. N is going to be N, oops, I can't do that right there. N is going to be N divided by L. Okay, but what I want to do is make this in the, I want it like that, right? So I'm going to change, I'm going to put this, that would be the, I want it in the XZ direction. I want it in the YZ direction. So I'm just going to do this, move the 0 over here, move the 0 over here, move the 0 over here, and that should do it. Let's see. There. There's my loop. Now it's the way I want it. I need to make a bunch of these, right? But what I want to do is to actually move the x value and make a different ones from negative L over 2 to L over 2. So let's do the following. I think this will work. So this is where I make that. I'm going to put, right here, I'm going to put theta equals 0, which I already did. But now I'm going to say, let's just say x is negative L over 2, and dx, let's see, do I want to, let's say nx is the number of loops in the x direction, I'll say is 10. So dx is going to be L over nx. So I need to know how far to move it each time. So while x is less than L over 2, make a loop. All right, so I'm going to tab indent this stuff. So I made a loop. But what I want to do is to start off, I'm going to have my x ring is going to be vector x0, 0. And so this Ri is going to be this thing plus x ring. Right, so I need to shift it over some. And then after I'm done with that, I'm going to move my x value. So x ring equals x ring plus vector dx 0, 0. I don't need that x. So let's call this x ring dot dx. Let's call this x ring. Yeah, x ring is actually a vector, but I think this will work. Let's run it and just see. And it didn't. X dot ring. Oh, x ring, I didn't. Vector. There. Okay, another error. X is not defined. X. Okay. Oh, you know what I did wrong? This is wrong. I need to get rid of that. Oof, caught it before it got too far. So yeah. Nope. Oh no, I think I've destroyed this. Okay, stop. Let's say x ring equals x ring plus dx. It should be doing it. Let's just print x ring. Let's see if it's doing something. Not just in a loop. No, see, it's stuck in an infinite loop. That's fine. Okay, so this happens sometimes when you do dumb stuff. Dumb things happen. So let's just open another browser because this has happened before. I'm going to open another browser, and I'm gonna start a new browser. So sometimes if you get in a loop, it like you're out. I'm not dealing with you again. Let's see if I can get it here. I might not be able to. There. Okay, so it's not saved though. So let's just click this. Let's just copy the whole code. I'm in a different account. And new trinket. Sorry about this. Life happens sometimes. And I'm going to paste it. I'm going to run it. And then I'm going to say solenoid. And I'll give you the right code. Don't worry about that. But we got it. We have our rings. Here's my solenoid. I'm pretty happy. That looks pretty great. That's great. Okay, now, and I did print out all my stuff, so that was good. So the moral of the story is don't make infinite loops. It will make you pay for it. You're paying for that. Okay. Now what I want to do is calculate the magnetic field at some location. I'm not going to plot the magnetic field everywhere. I'm going to make that for another video. But so we don't need this B scale. I already have this to calculate the magnetic field at some location. And it goes through my list of vectors. That doesn't change. Whether I have 1 ring or 10 rings, it doesn't matter. But what I do need to do right here, this I is not the I, right? I need I in dx. So it's going to be I times n times dx. Right, just like I said before, right? If I have 10 rings representing 1,000, each one of those is going to have a different number of things. Okay. So let's just go ahead and put RO is the vector. Let's put it at the center. We know that one. Vector 0, 0, 0. And I want to print B num. That's my numerical value. It's going to be B of RO. Now I want to calculate the theoretical version. Print B, let's call it Ampere. This is going to be equal to mu naught times n times I. That was right? Yeah. And then finally, let's calculate the other version. So I'm going to say, let's make this a function. Def B Z R-O T. Let's call it Z. Let's call it Z. I'm just going to give it one value, right? Let's call it D. That'll make more sense. Now what I want to do is say BT, my temporary one. I'm just going to type in this whole equation right here. So I have negative mu 0, that's a 0, times, let's see if I can get it right, I times n. And I'm using these global variables, and that's fine, divided by 2. I'm just going to multiply by 0.5, because I don't want to do parentheses, times d minus L over 2, d minus L over 2, divided by the square root of d minus L over 2 squared plus r squared. And then I need to do the same thing, minus d plus L over 2 divided by a square root d plus L over 2 squared plus r squared. Whew, that's a bunch of stuff right there. Oops, I wouldn't be surprised if there's an error, but if it is, we'll just move on. Return BT. You'll notice I do have stuff down there to make the full plot, but that's fine. Let's just call this BZ is going to be equal to BZ of RO dot X. Right, because I'm in the X direction here now. Let's see the damage we do. Didn't work. BZ, punctuation at line 45. Line 45. BZ, oh, that was, if that's all it was, goodness. Okay, it didn't get the last one, but this is, in the X direction, I have 800. Okay, that's not too far off, right? 1,000 or at 10,000 and 8,000. That's not bad. That's not bad. But what's the problem here? RO is not defined. Okay. RO. That's why. That's pretty good. That's pretty good. Let's move outside the ring. Let's see how well they agree. These two agree very well. Let's just move my RO up here to, oh, it is. Oh, I did it down here too. Okay, let's move it outside in the X direction of, let's say, L. No, they agree pretty well. I'm pretty happy. Okay, so we have this visual right here. We didn't draw an arrow. The numerical model, you can put that arrow wherever you want. It'll work wherever you want. Okay, so and I will display that. It shouldn't be too hard to add that on there, but we're already at 27 minutes. So if you made it this far, high five yourself. I will put a link to this code down below. The end. I'll talk to you later. That's it.